Good afternoon, everyone. I'm Jenna Myers, and welcome to the Climate Services Seminar Series. Before we get started with today's seminar, I wanted to go over a few logistics. This webinar will be recorded, and you can access it via the NWS Climate Services website after today at weather.gov/climate-services under the Resources tab. Also, if you have any questions, please use the questions pane to enter your questions, and we'll take them after the presentation. And now I'll hand it over to Fiona, the Climate Services Branch Chief, to make introduction of our speaker today.
And so welcome to our Climate Services Seminar Series, and we're happy today to offer this in partnership with the Space Weather Program. Today's seminar is titled Solar Variability and Climate Change, Specification and Projection, and our speaker is Dr. Judith Lean of the Space Science Division, Naval Research Laboratory in Washington, D.C. Dr. Lean is a senior scientist for Sun-Earth System Research in the Space Science Division of the Naval Research Laboratory, where she studies the integrated extended environment of the Earth from its surface to the Sun. She has a PhD in atmospheric physics from the University of Adelaide, Australia, and a Bachelor of Science from the Australian National University. And as a bit of background, she has worked at the Naval Research Laboratory since 1986, following an initial appointment as a research assistant at the University of Colorado in Boulder from 1981 to 86. She has numerous prestigious activities in her resume, including testifying to Congress on the role of solar output variations in climate change, chairing the National Research Council's working group on solar influences on global change, and serving on a number of NSF, NOAA, NRC, and NASA advisory committees. Dr. Lean was elected a Fellow of the American Geophysical Union. She's a member of the U.S. National Academy of Sciences and is a member of the American Philosophical Society. She's also the author or co-author of 150 published papers in the scientific literature and has made 300 presentations at scientific meetings, seminars, colloquia, and lectures. 2 of her papers were selected for publication in Geophysical Research Letters Top 40 edition, and she received the Presidential Rank Award for Meritorious Senior Professional in 2011. So with that, I'll welcome Dr. Lean, and please go ahead.
Okay, thank you. Hello, everyone. I hope you can hear me, even if you can't see me. And I'll try to point or to let you know where I'm pointing. So I'm really excited to be here because the topic of sun climate has been around for a long time, over 100 years, and it's very controversial. So what I'm going to present to you today is our current understanding of solar variability and how it affects climate. I'm going to start by talking about the Sun-Earth system. Let me see, which one do I press for the... Can I press this?
Let me see. No, I don't know if that one works. Probably have to press this one.
Okay, so when we think about sun and climate, we think about the sun's visible energy reaching the Earth's surface. But the sun provides energy for the entire Sun-Earth system. So I'm talking about sun climate, but there's also influences of the sun on the atmosphere, on the ionosphere, on space weather. So I'm just talking about a little part of this today. The energy from the sun dominates in the visible part of the spectrum, and most of that energy comes from and reaches the Earth's surface. That energy is then reflected or radiated to space, and it heats the Earth, so the Earth then emits infrared radiation to space. If the sun was constant and its energy constant, then we wouldn't care about it impacting climate. And in fact, for many years it was called the total energy from the sun, in other words, the spectrum integrator of all wavelengths, was called the solar constant. And in fact, it was a bit of a joke because someone, I remember way back at a meeting where someone said, well, if the sun wasn't constant, the meteorologists would have a really hard time because then they would have to forecast the sun in order to know or at least understand its impact on the Earth. Well, the sun isn't constant. It provides a forcing of climate change that we have to understand. The sun provides what's called the incoming shortwave energy to the Earth, and a whole variety of processes at the land and in the atmosphere take this energy, reflect it back to space, process it through absorption, photoionization, and the heating of the land itself then radiates back to space. So the sun is just the start of this. Understanding how its changes affect, say, the temperature at the Earth, which is like a net effect of all these other things, is very complicated, which is why it's been a controversial topic for a long time. One thing we've known for a long time is that the sun is an active cycle, and we know that through looking at sunspot numbers. That's the top curve. The sunspots show an 11-year cycle, but that doesn't mean that the sun's irradiance changes. But we now know through 40 years of space measurements that in fact the total solar irradiance, which is the integral over all wavelengths, which is shown in the middle curve, does change. It changes by about 1 or more watts per metre squared per solar cycle. So there's an 11-year cycle in irradiance. And people think, well, 0.1%, that's nothing. But the sun has so much energy that 0.1%, as I'll show you, is a decent amount of energy in terms of forcing the climate system. And you can see here that when the sunspot number is high, when the sun is active, the total solar irradiance is increased. Now we know that the reason for this is because the sun produces active region features. The sun has a cycle that's dominated by magnetic activity, a dynamo beneath the surface. This dynamo produces bright faculae and dark sunspots. And you can see in the bottom curve here that the net change in the total solar energy coming to the Earth is a balance between decreases in the energy when there are sunspots on the disk. So think of like a black mark on a light. It decreases the outgoing energy, plus bright faculae, which increase it. And you can see this competition here that produces the total solar irradiance variability. Now, the total solar irradiance is the integral over all wavelengths. That depends on wavelengths. So what I'm showing here, the blue curve is the spectrum, the solar spectrum, an average solar spectrum. The green curve is the variability of that spectrum in the 11-year cycle. And you can see that it depends strongly on wavelength. And in the visible spectrum, it's about 0.1%. Now, as I said, I'm not going to talk about space weather, but that would be affected by the energy shortward of 100 or so nanometers, which varies a lot more and dominates that part of the solar system. Now, because the faculae and the sunspots depend differently on wavelengths, they cause the sun to vary differently as a function of wavelength. So that's one thing. So the spectrum itself depends on wavelength. The variability depends on wavelength. And the deposition in the Earth's atmosphere also depends on wavelength. So in this curve, you can see that the green curve in the bottom panel is unit optical depth, which shows you the altitude where the sun's energy is deposited for an overhead sun. Most of the energy reaches the surface, and that's what drives climate, and that's what I'm going to mainly talk about today. But energy in the ultraviolet part of the spectrum is absorbed in the stratosphere, and this is what creates ozone. I'm going to touch on that briefly because the stratosphere is like the upper layer of the troposphere, and we can't really separate the system. People like to compartmentalize things into climate, stratosphere, ionosphere, but it's all one system, and there are vertical and radiative and dynamical and chemical processes that combine them all together. Now, the reason that we know that the total solar irradiance varies is because we've had a fantastic 40 years of space-based measurements, and the bottom curve shows that sequence of measurements. And right now, this time series is being carried forward by an instrument on the space station. And you can see that by all these overlapping measurements, they have different offsets because of their absolute calibration, but they all show an 11-year cycle. And if you look at in the different parts of the spectrum, it's a much more complicated picture. I'm just showing 3 different wavelengths here where the colored lines are the observations and the grey line is the model. Now you can see that the observations need to be adjusted for absolute calibration. Different observations have different trends. It's not exactly a database that a climate community or an Earth science community can use easily. So one of the things that we've done is develop models of the variability, and the grey line here is an example of that. And this is how those work. A model of the solar irradiance variability simply says that I know the irradiance will change because when there are sunspots on the disk, that will alter the irradiance, and when there are faculae on the disk, that will alter the irradiance. So the white curve here in the top panel are the total solar irradiance observations, which is just a composite of all those individual observations adjusted for their offsets. The green curve behind it is a model that basically takes the sunspot effect and the faculae effect. And you can see those two different competing effects there. You can do the same thing for the spectrum. So a climate model, for example, will need to know as input the spectrum of the sun's radiation from basically the far ultraviolet out into the infrared. And to make a model like that of climate variability, you have to then acknowledge that or take into account that the sunspots and the faculae depend on wavelength. So we've been able to do that with data and observations over the past 40 years to the point where I believe we're sufficiently comfortable in knowing the variability of the sun's total irradiance and spectral irradiance that we now have a climate data record that NOAA maintains. So you can go to the NOAA climate data record site and get the total irradiance and spectral irradiance basically every day. It's updated quarterly. So the difficulty though, I mean, we have 40 years of measurements and that informs our understanding of solar variability over 4 cycles. But what about going back in time, which is really important for climatology? I'm showing in these 3 panels here the total solar irradiance in the white curve, which is part of the climate data record. That is part of NOAA. You can see that in the last 3 or 4 cycles, the cycles were approximately constant. The most recent cycle 24 actually has a lower amplitude than cycle 23 and 22. Going back in time in the middle curve from 2000 back to 1650, that's the period where the sun's activity decreased from its current levels into what was called the Maunder minimum. That's a period when there were very few spots on the sun's disk, and it's an ongoing and unresolved question as to how much the irradiance changed during that time. In the climate data record shown here, there's a modest change in the background that suggests that the total solar irradiance during the Maunder minimum was about 0.5 watts per metre squared less than in the current minimum. Going back in time on the bottom curve, that's an example of some reconstructions of irradiance using cosmogenic isotopes because the paleoclimate community like the PMIC4 simulations, for example, need them. I'm showing you this because it's our current understanding, but it's speculative. The reason that it's speculative is we just don't have observations more than 40 years. But it's tied to the big question from a solar side, from a solar physics side, which is what did the sun do in the Maunder minimum? And so this is an estimate. All these little estimates here shown in blue are estimates that people have come up with for that value. And the yellow arrow is what is used in the climate data record going back in time. So I'm just showing this to make you aware that it's by no means known fully what the irradiance was in the past. And on the 2 curves here, you can see 2 different scenarios. One is that the sun simply has an 11-year cycle that goes back in time to the Maunder minimum. It had minimum amplitude in the Maunder minimum, as you see in the top curve on the right. Another is that there's a build-up of bright regions on the sun as it goes from a low activity state to a high activity state, and we've simulated this by what's shown in the bottom Earth flux transport model. So not to get into the weeds here, but I hope you understand that we do have a sense, a strong sense of how the sun's irradiance changes in the last 40 years, both spectrally and totally. It does change, and it changes at different wavelengths. And we can estimate within limits what that variability was over past centuries. So that's the solar side of things. The sun's irradiance varies. Because it varies, we need to know how much or how little. And there's a lot of work that says, well, I've looked at the sun and the climate and I don't really see much of a signal. That's actually not the point anymore, and I'll explain why I'm saying that. The point is to know whether or not, so that you can say, no, the sun is not causing this change that we're seeing, which is just as important as say the sun is causing this change. Now, the difficulty of understanding what the sun is doing to climate is because it's just one of many forcings. So solar variability, the changing irradiance, right, something that is going to keep on going and has been going. Volcanic eruptions, you can't control them either. Anthropogenic gases, including greenhouse gases, but also tropospheric aerosols from industrial activity that are in the troposphere, as opposed to the volcanic eruptions which produce aerosols in the stratosphere. Land cover changes, internal oscillations such as the El Nino Southern Oscillation, for example. All these things are causing climate to change simultaneously. Now, one way to pull out those different, or to try to pull out those different scenarios is to model the observations. And the white curve here is now the surface temperature observations. It's shown as an anomaly, so this time series has been deseasonalized. And because there are these, I think of them actually as rather arcane debates between NOAA and GIST and the Hadley Centre, I've used an average. Those observations are actually in much better agreement than people would have to think. But that is the average global surface temperature anomaly in white from those three different groups averaged. The orange curve is then a statistical model that reproduces those variations in terms of 4 different influences on surface temperature, one of which is the sun. The sun is shown in the bottom curve in green. You can see there's a modest cycle. It's about 1/10 of a degree at most, but in terms of the statistical significance, it's 100% significant. You can do multiple things to pull it out and test, add, replace, whatever. It is there in this record. You can see that from the cycle min to the max of the 11-year cycle, it's only a modest fraction of the overall greenhouse gas increase, its effect on climate over the past 30 years. But as Jim Hansen and Andy Lacis pointed out in 1979, for those of you who remember back then, they actually did a really nice paper called Sun, Greenhouse Gases and Climate. And they showed that over the period of the minimum to the maximum of the solar cycle, which you can see in this figure, for example, from 1996 to 2000, the change in the irradiance provides a forcing that's equal to the greenhouse gas forcing over that same time. Now, I'm talking about forcing, which is the energy change into the system. That's not the same as response. Response is how the climate responds to a cyclic forcing, such as by the sun, versus a monatomic forcing. But nevertheless, the change in the irradiance over this 5-year period is comparable to the forcing by greenhouse gases. But over short time periods, you can see months, for example, the biggest factors are the El Nino Southern Oscillation, which is shown as the pink curve, and volcanic aerosols. Now, the El Nino Southern Oscillation, you can see the big super ENSO in 1997, where you can see the warming, the global surface temperature went up by about 0.2 of a degree. You can also see Pinatubo in 1992, where there was a cooling of a few tenths of a degree. You can see that there was an El Nino event in 1982, but that was also coincided with El Chichon, and the two actually cancelled each other out. And that sort of shows how, if you look at this net record of temperature, you are integrating all these different effects. And so to know what's causing them, and ultimately to predict the future based on the predictors, you have to separate these out. So I want to point out too, in December 2015, there was a big El Nino, and I'm going to refer to that later, but you can see it here in the figure. Now, each of these different influences doesn't just, like the sun, some people think, well, the sun gets brighter, the surface temperature increases. That's not how it works. And you can see the map, the regional distribution of each of these influences here. The top pattern is what happens, how the surface temperature changes at the peak of the big El Nino, in this case in 1997. You can see, of course, as you expect, maximum warming in the Pacific, but also warming in the North Pacific and some modest warming all over the rest of the globe. And I think that's well known, that as time goes on, the ENSO signal propagates over the globe. When there's a big volcanic eruption, which is the second panel, it's fairly well known, I believe, that there's, for example, cooling in the following winter. So the regional signatures of these different factors, the third panel is the signature of the greenhouse gases, which is more uniform, but not by any means homogeneous, and the sun in the bottom panel. So these signatures are then all combining to alter the temperature at a particular site. So globally and regionally, all these different factors are causing the temperature to change. Now, in terms of understanding what the sun's changing radiation is doing, we can look at the bottom figure here on the left, which is a basic textbook figure that says the incoming energy from the sun basically is greatest at lower latitudes, right? Because the sun, heats basically at the equator, and less at higher latitudes because, there are times where there's no heating of the poles. The outgoing, and so the top figure shows you then the uniformity of that. Then the outgoing radiation, so the sun is heated, it radiates in the infrared around 10 micron or so, but the outgoing radiation has a different zonal mean distribution, and you can see that it's a more shallow equator to pole distribution than the incoming radiation. So the net effect is that the Earth tries to balance these, and that initiates the Hadley circulation cell, the ferrule cell, and the pole cell. The energy has to be transported from the equator to the poles to equilibrate the system. And that's how come we have these dynamical motions. And you can see that this establishes the intertropical convergence zone at the equator, establishes the mid-latitude synoptic regions at mid-latitudes. And if we look also in a longitudinal sense, the purple line is the intertropical convergence zone. The green lines are the flows of the jet streams. And for example, one of the early connections between solar variability and climate happened to be between solar activity and the both the location and the strength of hurricanes in the Atlantic, which makes sense because in the previous figure I showed you at the intersection of the Hadley and ferrule cells, that's where these mid-latitude synoptic features happen. Now, we know about changing the equator to pole gradient. Recently, we've had a lot of talk about that because the warming of the Arctic has reduced, well, we believe it's reduced that gradient. And what that does is alter the polar jet. And in the top, you can see when that gradient is strong, the little figure on the left shows a polar vortex that's quite robust and strong and contained. But when this meridional gradient weakens, and this is the work of Jennifer Francis, by the way, it sort of flops around a bit more. So that's what we know about that in the context of the Arctic warming, but a smaller version of that. And we think the same explanation applies, but at a lower level, is because of solar activity. It also changes this latitudinal gradient a little bit. And just to emphasize, if you remember, keep in mind this mid-latitude concept, if we go back to the pattern that I showed you about the surface temperature response to solar variability, you can see a number of enhanced paleo in the mid-latitude regions. And what I'm showing here is a compilation of many paleo reports about the solar activity and climate. It's like almost every, 6 months in Nature or Science, there'll be yet another paper about a relationship between, let's see, the monsoon in India, for example, or a cave in China or something like that, where they connect a variability indicator, a climate variability indicator, with climate as indicated by the carbon-14 cosmogenic isotopes going back. They all fit a pattern that matches the response pattern from the last 40 years. And the takeaway from this is that the sun's influence on climate does not influence the temperature uniformly. It rather drives changes in the circulation system, and that then affects things like different latitude regions, synoptic, mid-latitude synoptic regions, etc. The other takeaway is that if you see a big change, let's say you have an indicator at a location where you see a big solar signal, that doesn't mean that the whole globe is changing that way. So it's important to remember that a particular site doesn't indicate the globe. So that's the current understanding that we have of how we think the sun is changing the surface. Now that's a big part of the story, but as I said, the surface and atmosphere are also interrelated. So I also want to talk a little bit about the sun's role in the stratosphere. I just talked about how the energy from the visible radiation gets to the surface. I talked about changes that we see in surface temperature. The ultraviolet radiation from the sun below 300 nanometers is absorbed by ozone. In fact, it creates ozone to start with by dissociating molecular oxygen at wavelengths below 242 nanometers. And then the ozone that is created then absorbs ultraviolet radiation in the Hartley band 200 to 300. And that means that as a result of the sun, the temperature profile of the Earth, shown in the red, cools up to the middle of the troposphere, lower stratosphere, then starts warming again because of the heating due to ozone. And the ozone layer, you can see, resides there, peaking around 20-25 kilometers. So that is created by the sun, and therefore, remember I showed you that the variations of the sun's irradiance depends on wavelength, whereas the total solar irradiance from the visible radiation that reaches the surface varies by about 0.1% over the solar cycle. The ultraviolet radiation varies by an order of magnitude more. So we're seeing changes in like 20 kilometers above the surface now. Shown here on the left is the temperature from the MSU data, and shown on the right is the global total ozone. You can see completely different characteristics in these time series, these global time series, than I showed you at the surface. For one thing, just simply 20 kilometers above the surface. The temperature is cooling, and the ozone has been depleting originally, and now it's stabilized. But we can explain these again in terms of things like the sun, anthropogenic gases, in this case, not just the greenhouse gases, which cool the stratosphere, because once they get to the stratosphere, they don't have anything to block the radiation going out to space, so that cools the stratosphere. But also chlorofluorocarbons, which are ozone-destroying gases, play a role too in understanding this part of the atmosphere. You can see that volcanoes, whereas they cool the surface, at 20 kilometers, they warm the atmosphere at 20 kilometers. You can see when we get to just 20 kilometers, the solar cycle is now 0.3 of a degree instead of 1/10 of a degree. And if I kept going up to the thermosphere, 250, 300 kilometers, it would be orders of magnitude change due to the sun. You can see also the same similar thing in ozone. In both those bottom two figures, if you combine the chlorofluorocarbons, which is shown in as pink, and the greenhouse gases as the net anthropogenic effect, you can see that now the sun, simply at 20 kilometers in ozone, in other words, in composition and temperature, the sun is now about equivalent in magnitude to the anthropogenic gases. So the reason this is important is I've explained to you about what's happening in the troposphere, the energy flow there, how it drives the circulation cells. There's a different energy flow in the stratosphere where, because the sun basically heats this region through ozone heating, there's a more global scale circulation called the Brewer-Dobson circulation. And it sits on top of the Hadley Center. So the solar effect on climate, and a number of model simulations have confirmed this, there's a top-down heating of the surface, but there's also a top-down, bottom-up. There's coming from the effect of the sun on the ozone, coupling with the troposphere, and from the direct heating of the troposphere. So now we get into the interesting part of tying all this together. So I've told you about the sun's role in the surface, briefly in the troposphere, and at 20 kilometers. Okay. And I've explained to you how each of those net effects, those time series of anomalies, is the net effect of a number of different things, including the sun. So if you put all those together, this is a global temperature anomaly at 20 kilometers at the top, 5 kilometers, so middle troposphere, and global. You can see in the last 15 years, there is arguably no trend in the temperature. At the same time, the greenhouse gases have been increasing. Now, this led the IPCC in 2013 to make what I believe, and other people agree, was a major mistake in that, sorry, I'm prejudiced here, I'm proselytizing. They claimed that IPCC invoked a global warming hiatus in climate change because the reason is because if you look in the top figure on the right, the blue dots are the models by the general circulation models, all of the ones used in IPCC. They predicted that the global surface temperature would be going up for this period, whereas the observations shown in the red and the black did not. So IPCC was confronted with a challenge because at the time IPCC was being held, we were getting into 2013, the climate hadn't warmed for a good, 5 or 6 years. And people were saying, why are you telling me there's global warming when the climate hasn't warmed? And not only that, if you look at 5 kilometres, I could have showed you 2 kilometres, there's a lot of media attention that says the satellite record at 2 kilometres isn't showing warming. That means that there is no global warming. Okay, so how do we make sense of all this? Well, to start with, this is our cartoon interlude. I have some cartoons here about this whole issue. It's funny, but it's not funny because this is a really serious problem. The net effect that we've been addressing for the past, it's died down a lot now, and I'll explain why. But for a while there was a lot of talk of global warming as a scam. And it started off with, you can see this, this person here says, after 16 years of flat temperatures, and then they go on and on about all the things that people like to say, simple things about climate change. And so they say, see global warming. It's saying, no, we don't have global warming. The worst of it is that then, this is all from mainstream cartoons in mainstream media. Of course, just ask the global warming theory. So the sense is scientists who study climate change don't know what they're doing. And this then has economic consequences because Time magazine, this is a widespread publication. If we're having a climate pause, which people think of as a ceasing of global or cessation of global warming, why are we spending all this money to sort of for climate change mitigation, right? And this is the pause consensus. This is like, well, there isn't a pause. Yes, there is. I say it's this. I say it's the other. Okay, so this is the pause that's been characterising popular understanding and political understanding of climate change in the last 15 years. The Economist had probably the most interesting article. Who pressed the pause button? Right, so they talk about the slowing down, but then they say, a convincing explanation therefore matters, right? We need to understand what happened from 1997 or 2000 to 2013. And so they're talking about a paper that was published doing their best to provide an explanation. And it concludes, if indeed they do almost as good a job, if all were correct, the pause would now be explained twice over. In other words, there were so many papers explaining the pause is due to, the first one was the heat's hiding in the ocean. Another one was stratospheric aerosol, background aerosols are longer than we thought. Another one was it's aerosol burning in China. Many, many explanations. So here, from my simple statistical model, and this was published recently in WISE, which is the Wiley edition of climate change, you can do the numbers and put together the fact that from 2000 to 2011, that period, which is called the global warming hiatus, indeed, the observations in the model both show that statistically, there was no statistically significant trend. And I've put the trends there in both. The atmosphere at 5 kilometres had a more negative trend than at the surface, which is what we expect. But it was still within the uncertainties. But then you can look at the anthropogenic warming over this period. Anthropogenic warming kept going. There was no hiatus in anthropogenic warming. But what happened was, at various stages throughout this period, there was ENSO cooling, solar cooling, and a little bit of volcanic cooling. And the timing of all those things basically explains the pause. So you don't need to invoke heat hiding in the ocean. You don't need to invoke super amounts of stratospheric aerosols. And what's more, if you look at the patterns, you can see that the pattern is from 2000 on the top, on the left, 2001 to 2011. The pattern of observations and of the model, you can see the different effects, how they all came into play. So there was a net warming, it still kept going, but there was cooling in different regions due to these different effects. So in terms of the pause, it really wasn't a pause. Greenhouse gases didn't stop warming. The whole community and society and the public got completely upset about nothing, really. And the reason that they did that is because the models that the IPCC used to forecast into the future didn't have the capability to do the decadal variability, basically. And here's an example of that. On the two panels on the right are simulations by the NCAR Community Climate Model number 4. Now, this is a quite recent version of this model, and it's especially touted as one that can quite replicate ENSO. But if you read the paper about this, the way that they do this is they have to actually decrease the amount of aerosols in order to generate a decent ENSO, which means that they get more greenhouse gas warming, response to greenhouse gases. They overestimate the volcanic effect. They do a modest job on the solar cycle. But more than that, they don't get the ENSO timing. They may be able to reproduce something that looks like ENSO, but they don't do the timing. And none of the IPCC models do the ENSO timing. So none of them were able to replicate the pause. And I'm saying this because this really is this area between, the decadal time variability where people want to know what's happening and why it's happening, but the models that they're using don't have the ability to reproduce the natural variability, including by the sun. So what I want to show here is my long-term hero, who is not, he died, Stephen Schneider. He, in 1977, said a knowledge of the terrestrial climate response to a known solar variation, which we now have, could provide a gauge against which climate models could be calibrated. In other words, if you know how much the sun's radiation is changing, which we do, and you can extract, which I've shown here on the left, what you think is the response to that. Now, this is the statistical response. In the top, it's to ozone, and then temperature at various heights, and then at the surface. If you can calibrate a model with that, and on the right-hand side, the panels there are from the Goddard Institute for Space Physics Model 3, which is David Ryan's model. If you can get those patterns to match, then you can calibrate the models, and they're the only tool that we have for seriously estimating the future. So what I want to show here is what I think is the current state of that comparison between surface going up to ozone, statistically from the observations, compared with a climate model. The climate model is not doing too bad. This is just solar, remember. It's a whole other issue how well they do ENSO. But this is, I'm saying this because it's actually another role for why we want to understand solar variability as a calibration tool for testing the models. Now, back to the pause. Right, so I told you about December 2015, there was a big ENSO. In September 2015, the Hadley Centre, who should have known better, I might add, said, global warming hiatus could be coming to an end. Okay, everyone's, oh, okay. Then in the US, Washington Post said, scientists officially declared 2016 the hottest year in record. The community and the irregular person who reads the paper then thinks to themselves, oh, global warming's resumed. But that's not what happened at all. We just had another ENSO. And you can see here, I've shown the long-term climate record now over the past 150 years or 130 years in white. They're the anomalies. Blowing up at the top is just the period of the, quote, hiatus. We started it with an ENSO in 1979. It ended with an ENSO in 2015. But note, in the bottom curve, the ENSO itself in 2015 wasn't super duper, but it did occur at the peak of the solar cycle. So both the sun was increasing just a little bit, but enough to combine with ENSO to give us the warmest year on record, which has got nothing to do with the global warming, with the anthropogenic effect, which kept on going, just again, the natural variability. So, okay, so that's the pause, or the so-called pause that never happened. Had we been appreciative of decadal natural variability, none of that would have happened. So, given that we have an understanding of these multiple causes of climate change, not just greenhouse gases, and the fact that these things can cool and warm at different times, I'm now going to talk in the last part of my talk about projecting the future, which is like the holy grail of everything, basically. Basically, we have climate drivers. So that's the sun, volcanic aerosols, greenhouse gases. You could say that ENSO is a climate driver, an internal variability mechanism. And we have observations. As we, if we want to predict the future climate, if we have a relationship between the drivers and things like surface temperature, then we can predict the drivers, then we have a way to predict the future climate. And in fact, as observations go on, we can improve the models and improve the forecasts. The physical climate models need the drivers as well, although typically they only take into account the greenhouse gases, and some of them do the solar variability. So I'm going to show you some examples now of projections. The first thing we have to do to forecast, and I guess I should say project from our discussion earlier, I shouldn't be using forecasting, I should be using projecting climate drivers. The biggest thing is ENSO, and I'm sure everyone here knows more than I do that it's very difficult to forecast or predict or whatever, project ENSO in advance. So this is like a year in, I think that's 2018, many different models, many different sensors. But if you want to know decadal variability over the next year, 2, 3, 4, 5, you need to know what ENSO is doing. You also need to do what solar activity is doing. And so this is where the Prediction Center comes into it. They actually do forecast solar activity, but you then have to translate that into irradiance so you know what the forcing of the climate is. And you need to forecast greenhouse gases, or I say greenhouse gases, but what I really mean is the net anthropogenic effect, which is multiple types of greenhouse gases, including CO2, plus cooling by aerosols and a whole variety of things like black carbon. And shown in the bottom panel, RCP 4.5 is a representative concentration pathway scenario that was actually used for IPCC. But since then, the people at GIST, the Goddard Institute for Space Studies in New York, have come up with what they actually consider to be a better estimate. And for the projections that I'm going to show you, I'll actually use the average, like when in doubt, take an average. The other thing that's interesting in terms of projection is that in the statistical model, and I think this is physically true, the ENSO effect starts off in the Pacific, in the low latitude Pacific. But over time, the statistical model does best when it has lags of 5 and 9 months in addition to 0. So there's some innate predictability. If you know that there's a warming in the tropics, in the tropical Pacific, you can have a pattern, see in the middle panel, that would be 5 months later and then 9 months later. So there's some inherent predictability in the fact that ENSO has its own sort of, it doesn't just come up and go away. It has a longer term impact. So the challenge of decadal forecasting, had the models been able to, or the community been able to forecast decadal climate better, we would not have had the whole fiasco of the hiatus. The Hadley Centre has begun what they call an international climate forecast decadal exchange. And after the IPCC in 2013, they realised that many of these models were all sort of, they weren't operational, but they were geared up in there were maybe a dozen groups who were making forecasts. So they decided, let's have an informal exchange where every group projects surface temperature, and they also do rainfall, precipitation and things, for the next 10 years. We've been doing this for 7 years so far. It's really actually an interesting exercise. They have a website. It was initiated in 2011. There was a paper about it in Climate Dynamics. And most recently, the WMO endorsed it as an official program. And I believe the way the Hadley Centre, who's mainly Doug Smith and Anna Skay, view this, is as a test bed for, how well can we really get a handle on forecasting the climate or temperature, whatever, for the next year. And so here are some examples, and this is like where the rubber meets the road, so to speak. These are the predictions made in 2016 for the annual temperature in 2017. So it's 1 year forecast. The top left is the average. The top right is the Canadian Community Climate Model, GFDL, a whole variety of different models that you see. And the NRL is the statistical model that I've just been telling you about. There are other models as well. On the bottom right is the actual observations. So if you compare the bottom right with all those different predictions, that's how well we can forecast surface temperature 1 year in advance. And it's not great. So what I'm going to show you now is the skill with which you can do that on a 1 year basis, just for the NRL part of it, right? So all these different groups submit their forecasts and they all are working on it themselves. But I've been working with the statistical model, and shown here in the white are the surface temperature anomalies. And each of those different colours is a different prediction made, starting in 2011 for 2012, etc., etc. In fact, we just did the last one now, so that would be the 8th one. The drift in the coloured lines is how those predictions of the next 10 years have evolved as the predictions have been made. And to look at it in a different way, the 1 year forecasts. The observations on the left, top left, the observations are in green. In fact, the observations are in green in all its panels. The forecast for the 1 year forecast is shown in blue, right? And these are anomalies. Relative to persistence, shown in whatever, watermelon. Persistence is when you say next year's got to be the same as this year. Climatology, it's a 10-year climatology which says next year is going to be the same as the last 10 years. So you can look at the anomalies and calculate the skill score. So for the 1 year forecast, are 53% improved relative to persistence, and I think it's 67% relative to climatology. And then on the other side are the 5 year forecast. So just including a little bit of information about the decadal variability, and especially, of course, the greenhouse gases, which is dominating things, you can get at least an improvement over persistence and climatology. This is ongoing, and eventually the Hadley Centre is going to be analysing all those data regionally as well as globally. So I'm getting near the end now, what to expect in the future. So everything I've said hopefully has made you aware that there's more happening on a decadal timescale than just greenhouse gas forcing, which causes warming. And on the left here, I've put together in the top left scenarios for the El Nino Southern Oscillation. I've assumed we'll have a volcanic eruption in 2040, anthropogenic curve, greenhouse gases keep warming, the sun does its 11-year cycle. These are the forcings. You can see that the sun there is modest, but it's still there. If you put them all together, if this is how these forcings really play out in the next 20 years, you could have another pause. But if you put them together in a different way, you could have what I can imagine people in the future saying, global warming's accelerating. My goodness, the temperature's warming much more than we thought from greenhouse gases. None of this has anything to do, the rates of change aren't anything to do with the greenhouse gases. It's how the decadal variability either mitigates it or exacerbates it. So going forward, until we understand decadal variability, we could easily have another pause scenario, or we could have a super warming scenario. Another thing in terms of the surface temperature projections is I showed you the global signature. It's also going to affect the regional signatures. So here are some projections going forward. If you just include greenhouse gases and the sun, which is the time with the time series shown on the bottom, these are the surface temperature changes that you would get. But if you then include some real ENSO variability, you get quite different, or you can get different regional effects. So this is important regionally. And the same thing is true for the stratosphere, the lower stratosphere, different effects depending on what happens in terms of the natural variability. Okay, so this is my last slide, and I need to address this because in addition to a lot of media and scientific publications about the pause or the hiatus, there are also periodically, you'll see from time to time, claims that the sun is going into a Maunder minimum, or at least it's going into a state of low activity, and maybe this can affect climate. Maybe it can cancel climate warming. So the Capital Weather Gang, does everyone listens to Jason's seminar, right? Yeah, he's great. So he talked with me about this, and he wrote an article about exactly this topic. Could a quiet sun cancel global warming? So in the top left, you can see that I've projected into the future a time series of surface temperature stimulated by increasing greenhouse gases and the solar cycle. And the solar cycle is just that wheel on top. Now, remember I said that we don't really know how much the sun's radiation was lower in the Maunder minimum. So if the sun does go into a Maunder minimum, we don't really know how cool it's going to get, but we know it's probably not going to be more than 1 or 2 times the solar cycle. If the decrease was 1 times the solar cycle, that's the green curve, we get down to 1/10 of a degree below what the temperature would be with the greenhouse warming. In other words, that trend into the Maunder minimum would, by 2030, would just be a 1/10 of a degree cooling. So it's really nothing compared to what we expect from greenhouse gases. Even if it was 5 times the solar cycle, in 2030, we would still be no warmer than we are now. So the sun is not able to cool the climate enough to make Maunder minimum little ice age temperatures recur. And furthermore, the people who claim this, and this is a typical case of solar physicists being over enthusiastic about the Maunder minimum, but if you look at the long-time carbon-14 record, which is a cosmogenic isotope record that shows solar activity in the past, people like Ken McCracken and Jörg Beer have shown there's actually a 2,400-year period in the occurrences of minima. In this record, the minima are those dips in the bottom. We just had a Maunder, Spora and Dalton minima 350 years ago. So the likelihood of having more minima in the future is not high. So when you see these things in the media, the sun is going into Maunder minimum, the cycle's stopping, we could have, will this cancel global warming? It won't. So, in summary, solar variability and climate. The first thing that I've talked about, and hopefully everyone appreciates, is that the sun's irradiance changes. It's the forcing of climate. It changes on multiple time scales. You can't neglect it, even though you could argue that it's a minimal influence. Part of knowing what it does is being able to answer the critics who say the sun is doing everything. You need to know what it is doing and what it isn't doing. It produces climate forcing of the entire solar system, but that's a whole other different series of talks. The observations only exist for 40 years. They're being continued. They're part of NOAA climate data record, is part of this long-term reanalysis of past records and ongoing maintenance of future records. We understand the variability. We believe it comes from spots and faculae, at least on decadal timescales. Whether or not there are larger changes in the solar dynamo on multi-centennial timescales, we don't know. There are large uncertainties in the magnitude going back in time. But we can put constraints on it, at least. The solar forcing can occur simultaneously with multiple other things. So it's very hard to pull out the solar signal. If, for example, you just say, I'm only going to look at solar max shears or solar min. If there was a volcano or an ENSO at that time, then you're perturbing your sample. But you can pull out statistically these different influences. And you find this modest but significant solar signal that increases in amplitude as you go up through the atmosphere. Climate forecast 1 to 10 years ahead, I think that's a really exciting area. It seems to me that people are interested in this. And going to those timescales, you need to be able to forecast the sun and ENSO, and who knows if you can forecast volcanic activity. At least with ENSO and the sun, you have a little bit of persistence. So anyway, good luck to the climate forecasters. That's all.
All right, thank you so much, Judith. Do we have any questions in the room here? And if you do, can we speak kind of loudly so the mic can hear? Otherwise, I can repeat your question too. Marina?
I realize, believe that there is a relationship between ENSO and sunspot activities. Can you elaborate anything?
Yeah, I can.
There's a relationship between ENSO and sunspot activities.
Okay, so ENSO is variable, the timing and the amplitude, right? There are also, like Kevin Trenberth is a great advocate of changes in ENSO with greenhouse gases, for example. And so people have looked at changes in ENSO with the sun. It's very ambiguous, but there's a sense that somehow or other the state of the sun is affecting ENSO. The most definitive study, I think, on that was a study that Mike Mann and a number of people did in the paleoclimate record, and they looked at paleo indices of ENSO, and they found that a positive forcing light by the sun, also by greenhouse gases, produces a La Nina type distribution in the Pacific. So that the sense is that when the forcing is higher, the distribution in the Pacific is more La Nina-like. But it's not a La Nina, it's just that that's the way the balance between the heating of the Western Warm Pool and the Pacific and the Eastern Pacific alters or changes interacting with the Southern Oscillation depending on solar activity. So I think how anything affects ENSO is uncertain, and it's another layer of complication. Like in all the modelling I showed you, it's assuming those things are independent. And I don't know the answer, but the sense from the paleoclimate community is that the sun produces a La Nina light distribution, but people like Kevin Tremblay say positive forcing produces more ENSO. So I don't know, work on it. It's an amazing question. It's a similar one to we were talking about earlier about the QBO and the sun.
Another thing, maybe we can learn something from the near past, like medieval warming and little ice age, because there is records from that.
Right. Well, in the, I think in one of the papers I referenced, I did a review on sun climate for Oxford Research Encyclopedia, and I think there's a paper that Mike Mann also did showing, looking at patterns in the little ice age and relating them to different forces.
Quickly, before I get to the rest of the people in the room, if you have a question online, just type it into your questions pane, and then we can read it here. Other questions?
Oh, it's so clear, right?
You actually, for me, you wrapped it up in the last slide. I was actually going to ask about, like, if the solar activity was low again, could we expect to see another cool period? But you kind of...
Okay, I anticipated your question.
Yes, you did.
That's very frustrating for the people, my climate science friends, when they see a solar person. The solar people have dynamo models of the sun's dynamo, which is the driver of activity, and they run their dynamo models. And, oh, look, we get a more de minimum. It happens this often. And, oh, it must be affecting the climate. We're going to have a little ice age. And the climate people are so frustrated because it's like, no, the little ice age is much more complicated than that.
Right. So if we take away anthropogenic effects, how long of a period would we need to get to see changes in temperature? Like how long was the morning
from
minimum?
The sun? Oh, so the morning minimum occurred 1645 to 1715. So that was 300 and so years ago. So we believe we've been in the Assini phase. So before that, though, just 100 years was a spora minimum. So it could be maybe 50 or 100 years. That's another thing. The figure I showed you, I had it happening within 20 years. But in effect, if the sun went into a morning minimum, it would take longer. But the reason, so the whole prediction of solar activity is very uncertain, right? So Jimmy can tell you about that. But a couple of years ago, the solar physics community had a big conference, and they said, or maybe it was 10 years ago, they said, we're not going, it was 10 years ago, because they said, we're not going to have cycle 24. The sun's, all the indicators that we have, so this must have been back in 2008, 2010, a very long minimum, right? And there was a whole lot of things about the sun's going into a quiet period. And the solar people said, it's possible we won't even have solar cycle 24. But solar cycle 24 came, and it wasn't as big as solar cycle 23, but it was about half the size. And so we did. So they were wrong. But there's a lot of this catastrophic, forecasting that gets them a lot of attention, but and makes people sit up and notice, but it's not really right.
I have another question, if I may. How about melancholy cycles? How they will be with anthropogenic forcing changing the climate? Because there would be some variations, I think, coming up sometime.
Okay, so you need to get Bill Rudderman here to give you a seminar on that, because he's an expert on that. My understanding is that over the last 150 years, the Milankovitch forcing is minimal.
Right.
But in principle, yes, on longer timescales, you would include that. The interesting thing about the Milankovitch forcing is that there's cycles at, I think, 21,000 years, 40 and 100,000 years, I believe. They can do the 21, 23, this is getting a bit out of my depth here, and the 40 reasonably well, but the 100,000 year cycle is due to the eccentricity, so it's really a sun distant effect, and they can't do that. And I think there might be a relationship between the models not being able to really do a proper response to solar irradiance variability either, which is in a way a similar thing. But that's way beyond what I can answer.
Okay. Well, I think we're good here. All right. Oh, is it? Oh, I guess we're over our time anyways. Okay. Well, thank you so much. That was very interesting. And what we're going to do is we're going to put the recording up online again at weather.gov/climate services under the resources tab. All right. Thank you, guys. Thank you to our speaker, Judith. And thank you for all our online audience.
Tell you this.
All right. Have a good day, everyone.